Thank you, Eugenia and Marcus. So this will begin the data analytics track, which will be chaired by myself, Seth Nemeshor from Brookhaven National Laboratory, and Manuel Gonzalez from CERN. As this is the last day of the conference, I would like to take the opportunity to thank the organizing committee for putting together this successful conference, and especially given the difficult and extraordinary circumstances. So there will be hopefully 5 talks in this data analytics session, which we will hope you find interesting. As a reminder to the delegates, please ask questions by raising your hand in Zoom, or posting in the Q&A area of Zoom, or by asking your question in the Q&A area of Whova. If we don't get to answer all of the questions, we'll request that the speakers respond online. For the speakers, you will have 12 minutes to speak and another 3 minutes for questions, and we will remind you 2 minutes before the end of that time limit. And at this point, I will hand it over to Manuel to introduce our first speaker. Thanks.
So hi, everyone. Our first speaker is Alex Saoulis. He's from the Science and Technology Facilities Council of the Rutherford Appleton Laboratory in the UK. So Alex is an accelerator controls applications graduate. His work includes developing software to help with the ICES accelerator controls transition to EPICS. And he's using machine learning for various applications across the facility. And he's going to tell us today about machine learning for anomaly detection in continuous signals. So Alex, share your screen.
Great, thank you. Can you see that okay?
Yes, perfect.
Great, all right. Thank you for the introduction, Manuel. Today I'm going to be talking about machine learning for anomaly detection in continuous signals. So specifically, we're going to be looking at applying supervised machine learning for anomaly detection. So in the presentation, we're going to be looking at the case where all we have is continuous raw time series data without labels. So I'm going to briefly step through data preparation. We're going to have to go through a process of data labeling. We're then going to look at model training, so training and evaluating a couple of different ML models, and then finally a brief look at deployment. So the case study we'll be looking at is the ICES Target Station 1 liquid methane moderator. So TS1 is used to generate neutrons through a spallation process, and these neutrons have to be moderated for suitable energy spectra to perform neutron scattering experiments. But for usable data and downstream instruments, we need very stable temperature in the moderators. And irradiation of the liquid methane moderator releases hydrogen, which causes flow and therefore temperature variability. So that can make downstream instrument data unusable. So it's important we basically work with the operators very quickly to fix these issues when they crop up. Unfortunately, we have no logbooks or digital signals that record anomalies in the historic data. So we're basically going to have to go through that process of labeling in order to apply supervised machine learning. And we're just going to be classifying between normal operation or anomalies. Okay, so briefly, data preparation. So the raw data, so recently ICES accelerator controls have undergone several software upgrades, which have allowed us to store a large number of time series signals from across the facility in a database named InfluxDB. The signals are recorded every 2 to 3 seconds, anytime a value is changed. And we're going to be focusing on a signal called TC68M, which is located by the liquid methane. We use pandas to basically filter out periods of bad and out-cycled data to downsample the raw data and account for long-term signal drift. Then briefly feature vector generation. So we did a bit of data exploration to figure out over what sort of timescales the anomalies appeared. It seemed generally between 1 and 2 hours, and that you could get very rapid oscillations and spikes over shorter time spans. So we settled on downsampling to bin lengths of 20 seconds in order to preserve the granularity of those rapid oscillations, and feature vectors lasting 90 minutes, giving feature vectors of dimension 270. Another important consideration is we wanted to evaluate models constantly during live operation. So we basically had to randomly sample from our historic data in order to get something that would be representative of real-time evaluation that we could train our models on. And going through 2 years of data gave around 4,300 data points, each covering a unique 1.5 hour window of the data. Okay, so labeling the data. So again, in order to do supervised learning, we need class labels for each feature vector. And we've got 4,300 feature vectors, no class labels. And to do something like this manually would obviously be extremely tedious, require a lot of expert time and effort. So what we ended up doing was using a method known as TSNE to do dimensionality reduction and clustering, as well as dynamic time warping to be used as a metric for calculating similarities. And you can see a couple of unlabeled data points here that we need to process. So TSNE, as I mentioned, it's a popular dimensionality reduction or clustering technique, and it basically works by taking a pairwise similarity matrix between all our high dimensional features and reproducing those those similarities in a low dimensional embedding. So this example here is from the classic MNIST digits dataset. You can see the features up in the top right. And then we have a couple of well-known techniques for dimensionality reduction. So PCA, the latent space of an autoencoder, and then visualization by TSNE. And you can see the TSNE plot, you've got very clear, distinct clusters forming for all the different classes. There's also a number of disadvantages with TSNE. For one, there are hyperparameters, which means that there's a hyperparameter tuning process involved. That can be a bit painstaking. And also it's a non-parametric algorithm, which basically means that unlike something like PCA, it doesn't produce a mathematical formula which can embed high dimensional data into the low dimensional space. And this just means that we can't, well, if we ever want to add new data points to our low dimensional embedding, we need to run the whole algorithm again. So we can't just embed things anytime we want. Okay, then in order to apply TSNE to our time series data, we actually had to come up with a similarity metric. So the standard method would be to use Euclidean distances, but we've been randomly sampling our time series. There's no preset start and endpoints, and that means we get misaligned time series. So you can see these two features. They look very similar, but using a Euclidean distance could give you very different similarity scores. So we have to come up with something better. We use this dynamic time warping algorithm instead, and that's basically something tailored for these misaligned time series. So dynamic time warping, it basically searches for an optimal match between two time series, and it does this by non-linearly warping along the time axis and minimizing some cost function. And so you can see the same two feature vectors on the right-hand side now. We're basically finding points in the two time series that match and then take the Euclidean distance between them. And that actually gives you a much better estimate for the similarity between two misaligned time series. Okay, and now we can actually apply TSNE and dynamic time warping to our data set. So we generate the pairwise similarity matrix for the whole data set at once. This is quite a computationally expensive step. And then we can run the TSNE algorithm many different times at different hyperparameters and then explore the low dimensional embedding with an interactive plotter. So we do this interactive plotting to basically figure out when we've got an embedding that will work well for us and will allow us to label the data set quite quickly. So we repeat this until we get two large-scale distinct clusters, as you can sort of see on the right-hand side. And this plot on the right-hand side is all 4,300 of our feature vectors embedded in this 2D map. And you can see two broad classes emerging. Okay, and then once we've done this, we can continue to explore with our interactive plotter and manually define cutoff boundaries in the embedded space in order to make a first order approximation of the feature vector labels. So after you've done this, you can then use the interactive plotter to start improving on your first order approximation to improve on that first pass. For more complicated problems, you could use something like k-means or Gaussian mixture modeling to do this, but for something as simple as this, it sufficed to basically just draw the lines on ourselves and then manually make changes around the edges. Okay, and then this is a very brief demo of what this interactive plotter looks like. So you can select a point in the 2D embedding and then see the corresponding feature vector and then make manual changes to the labels for anything incorrectly labeled. Okay, great. And now we have labeled data. So here's the same representative sample of a bunch of different feature vectors from our data. And you can see that now we have labeled data, which means we can apply supervised machine learning algorithms to it. Okay, so supervised learning. We use the TensorFlow and Keras Python frameworks to do all of the machine learning. For hyperparameter tuning, we basically split our data set into a training set and a validation set. And then the validation set is basically used to allow us to tune different hyperparameters for all of our different models. And then we have a holdout test set, about 20% of the data that we use for a good estimate for an out of sample accuracy. So we use neural network models for our classification task. We had a feed-forward neural network, an attention-based LSTM, and a convolutional neural network. Each of these have the fixed input layer of 270 length, and then a softmax output layer of length 2, which basically outputs the probability of a feature vector belonging to either the normal operation class or the anomaly class. Okay, so first, the feed-forward neural network. This is the simplest neural network architecture. So basically just a multi-layer perceptron with a softmax output layer. You can see the train. So after a period of hyperparameter tuning, we settled on this architecture on the slide. And this serves as a simple baseline model. Since feed-forward neural networks learn relationship between specific elements in an input vector, they're not particularly well suited to time series with no preset start and endpoints, with misaligned features within the input, and so on. So you don't expect it to be well suited to time series, but it should generally perform fine for simple problems since general relationships can still be learned. Okay, the next architecture that we looked at was the attention-based LSTM. So this is an adaptation of the long short-term memory network. So the LSTM basically processes an input vector in temporal order, which allows you to sort of preserve the causal structure of your input. So this is well suited for time series, natural language processing and stuff like that. And then the attention layer on top of that basically improves the ability of the LSTM to learn long-term dependencies between features in your input feature vector. The attention layer also has the added benefit of providing some level of explainability to your model, which we'll go into briefly in a second. Finally, the CNN, convolutional neural network. These are typically used for image data, but they can also be used as 1D convolutional layers for time series classification. So again, the hyperparameters are shown on the screen. The reason CNNs are well suited to this problem is basically they learn shapes and edges in an input time series to identify whether something is an anomaly or not. And this is actually very well suited to what we're looking at, since we basically look at sort of misaligned time series with no preset start and endpoints. And so we want something that's able to deal with translational invariance well and is able to classify features no matter where they appear in the time series. So CNNs are actually a good fit for this problem. Okay, and now finally, we evaluate each of these models on our holdout test set to see how we expect them to perform in real time. And these are the results. We've got basically the CNN performs the best, but actually not much better than the feed-forward network. And on further analysis, turns out that the majority of the misclassifications, especially for the CNN, was basically just bad labels. So it's just the CNN outperforming the labeling process, which is going to inherently be noisy. And you can see a couple of examples here. So something like this time series here, an operator might have wanted to classify it as an anomaly, and the ground truth given in the bracket says that it was a normal. So there are still problems with the labeling process, but that's to be expected. It's never going to be 100% perfect. Finally, explainability. So as I mentioned earlier, attention, so ALSTMs, you can use the attention activations in the network to basically build a picture of what parts of the time series it's paying most attention to, and that can be used to help explain why a neural network has made a decision that it has made. So similar with CNNs, you can use saliency maps or occlusion masks to do a similar thing. And I think these sorts of things these techniques would be most useful for operators in more complex problems where it's not immediately obvious why a network is making the decision or classification that it has done. And finally, let's look at deployment. So we basically designed a data analysis layer that sat on top of the existing ICIS accelerated controls. So the models were evaluated in this data analysis layer using rolling feature vectors where bins were generated every 20 seconds. The outputs of the models were fed back into our network and then were displayed in a live dashboard that operators could use. And after some time, we also introduced some alarms in the system, which were passed back to our control system, and they were displayed in the main control room. And this is what the Grafana dashboard looks like. You can see the models being evaluated in the top left and a bunch of other diagnostic operational data. Yeah, and I will stop there. So thank you. Are there any questions?
Thanks a lot, Alex, for the very nice presentation. We have a bit of time. We know already there is a talk missing, so there's quite some time for questions, if there are questions from the audience.
So we have one in the Q&A session.
Yeah, but there are two. One from Ignacio Lopez. He's asking, how do you select your 20% holdout sample? Is this the only validation you have for the models?
So the 20% holdout sample is basically taken randomly from the data set. So when you're training your models, that definitely is the only validation you have. But then we did a lot of testing on the live system with these models, running it in the dashboard and generating alarms and then checking whether those alarms are valid or not.
Okay. There is also a question from Gabriela Sopardi. She's asking, sorry, not sure if you explained this already. Are you automatically labeling your data set?
So the labeling of the data set is partially automated, I would say. So using this TSNE, which generates these nice clusters, we're able to effectively label, I'd say, 80 to 90% of the data set very easily, just by drawing these two lines. And then, well, I'd say even more than that. I probably had to manually label about 100 to 150 data points myself. And yeah, so what that means is that once you've drawn these two lines on, you've labeled almost all of it, you have to do a little bit of manual labeling to check for any issues, but it cuts out a huge amount of that process.
Okay, there is one further question by Michal Piekarski from Solaris. He's asking, have you encountered the problem of unbalanced classes in the data set? What was the number of anomalies in the data set compared to the non-anomalies?
Yeah, that's a very good question. So we did have a minor data imbalance. So I think it was sort of about 3 times as many normal operation to anomalies. This wasn't actually a huge problem. So just by reweighting things in the training process, it wasn't a problem. But in some of the future work that I did on anomaly prediction, there was a much worse class imbalance, and that does become a problem. So I think supervised learning can fall down a little bit if you have very, very unbalanced data sets.
And there is a last one. We'll take this as the last one by Antonin Sulk from DESE. He's thanking you for this presentation, and he's asking, how do you decide how many classes do you want to use?
That's another good question. So that was basically decided for us by the operators, so the people who actually wanted the anomaly detection. They were mainly just interested in bit flagging anytime there was an anomaly. And so for us, it was a simple choice. You just normal operation or anomaly. But I think, yeah, it depends on what your users want, whoever's wanting to do this anomaly detection.
Okay, so many thanks again, Alex, for the presentation and all the answers to the questions. We move on to the next speaker, which in fact we are going to have to jump. Second speaker, I think is not, Seth can confirm, but I don't think it's connected. Yes.
So our second speaker is supposed to be Thomas Chen, but he is not with us today. So we also, the third speaker, Ali Kalegi, is having some technical issues. So we will move his talk to the end of this session. So instead, we're going to move on to what is supposed to be the fourth talk by Zdeněk Matej. And Zdeněk is a scientific software developer at Max IV Synchrotron Laboratory in Sweden. He will speak about how they're using FPGAs for high-level processing of data from fast X-ray cameras, in particular about data reduction of images from X-ray scattering and diffraction experiments. Thanks. So share your screen.
Hi, welcome to everybody. I'm preparing my slides quickly. Sorry. Now I can share my screen. Desktop 2.
Looks good.
It's good. You can see my screen, but no, not me. Okay. So I will maybe need to go here. That's bad. Okay. So I would like to introduce our FPGA data analysis project. There is a collaboration of several researchers from Max IV Laboratory and from Niels Bohr Institute in Copenhagen, Denmark, funded by Essence Foundation. As I said, we are Synchrotron Laboratory. so we have hard X-ray beamlines. On hard X-ray beamlines, there are photon beams hitting samples that are scattering around, and they hit hard X-ray cameras and detectors. And these detectors are catching frames like pictures like depicted on the slide. Right? There are some patterns, usually rings or dots. And we would like to analyze or basically process this data. So outline of our presentation is that I will describe one method of processing of this data. I will give a motivation why I would like to do this with FPGAs. Then I will describe non-FPGA algorithms and FPGA, and then I will switch to FPGAs. I will show some performance figures and maybe give some other examples if there is time. So, we could just pick up a piece of the detector, ROE, make a projection, and we would get a similar signal. But this is imprecise, and it is also little using just a small part of the detector. This is why we would like to average the signal over the whole all azimuthal angles, which is called azimuthal integration. The first part of this problem is geometrical, as we need to calculate a scattering angle, and from this scattering angle we can, and this influences later peak positions, which then influences the distances is in the determinate sample. So for example, nowadays, as Avogadro constant is defined by number of atoms in a big silicon crystal. And if you want to measure precisely lattice constant of the silicon crystal, you have to do similar things very precisely on very many decimal places. Then, of course, discrepancies in geometrical calculations can influence peak width and resolution. Then we have some requirements from physics where we need to apply very precise intensity corrections because they will influence hence the shape of molecules determined from the data. Then there are experimental requirements. We need often oversampling in order to keep resolution, which results then in need of pixel splitting. We need to do also error estimates. And there are some technical requirements, and some of them are like, we need to deal with a very wide dynamical range, already in the original pictures. And the technique is increasing the dynamic range by 3 orders of magnitude. So it's really picking up noise, like signal from noise. There is high data compression, and we have high data rates. I just wanted to say that we today have a megapixel cameras running on kilohertz frame rates, which I am giving one measure. I would like to have about 3 gigapixels per second for real-time applications. So, here is how the azimuthal procedure works. We calculate the scattering angle. This we convert to a linear index into the output array. We correct the intensities of pixels in the image, and then we can move at this corrected intensity into the output histogram. So it's binning or histogramming. If we have a series of 2D images, we can do a series of these such patterns that are results of this bin counting, and then we can assemble them again in 2D image, and we can, for example, follow a chemical reaction as it is depicted on this picture, where we follow a thermal decomposition of potassium chloride that is filled in the capillary in this picture, and there is at some point oxidation or explosion almost. Also, that's a nice experiment. What is interesting is that we see everything very well, but with this small detector we have only limited view. And unfortunately, in the most interesting case, we don't see a signal from amorphous and pluricrystalline matter. That we could see with a much larger detector that is slow. So in real experiment, we could, for example, couple this small camera that is very fast with a larger camera that is slow over a real-time processing in FPGA with a fixed latency, and use this as a trigger for our experiment. So, I said that I already described the geometrical and physical part of the azimuthal integration, and now how we calculate it. As I indicated, geometrical and physical part can be divided, and then it is simple histogramming or bin counting. So one could in fact use a NumPy bin count function that is fully sufficient for this. one just needs to run it twice. For the second time, it needs to be run for normalization purposes and error estimation. Another alternative is to use a sparse metric multiplication, where the like corrections and weights in case of pixel splitting are coefficients of the sparse matrix. Yeah, that has a shape of the number of like output bins that we have, that are thousands usually. Yeah, and the number of columns is the number of pixels that we have, that are millions. So it's very rectangular matrix. Yeah, this matrix has about millions of non-zeros, because this is like a number of pixels multiplied by how many we are splitting a pixel. If we are splitting pixels, sometimes we have to do it. So that's a mathematics on CPU. It's extremely simple. So you can see that you can do this with NumPy. And there is a lot of software implementing this on CPUs, some of them also on GPUs. You can see that several facilities, these always came with several softwares. Some of them are fast, some of them are slower, some of them have nice GUIs, and other ones have a nice calibration tools. Some of them are dedicated to special type of experiments. So that is, it's not like competition. It's like it's sometimes good that there is flexibility. Some of them are using different algorithms. And for example, Matfreya is clearly using sparse matrix multiplication, which is equivalent to bin count. Yeah, it's a contribution of Aarhus University in Denmark to Max4. Some of them have even benchmarks and are running on GPUs. Using, for example, this benchmark and other tools, I have assembled a small table where I'm just indicating that with decent nowadays GPUs, one could achieve like pixel rate processing about 3 to 6 gigapixels per second, which is quite good. With CPUs, it is worse. But if you have a very like multi-core machine, you could also get to similar numbers like gigapixels, which is not bad. So here I am ending with CPUs, and I go to FPGAs. So the first implementation on FPGA was done by my collaborators, Karl and Kenneth, with their framework called synchronous message exchange. They did it in less than 1 day, and they implemented it for integers. The algorithm that they were using were at the end very similar, which is, for example, in the book called The High-Level Synthesis for FPGAs, and it is depicted on the picture from that book. It is a simple algorithm. Output is stored in a local memory, BRAMs, and every cycle we are comparing the positions, the target position for the new and old values. If they are same, we are accumulating value in accumulator. If they are different, we store the value in the local memory, we fetch a new value and store it and accumulate it in accumulator. So this is simple histogramming. It is very well-known algorithms for FPGAs, and it works well on integers. The performance with FPGAs is also very good with cheap FPGAs and SOCs, like $100 ones. You can achieve even gigapixel per second for integers. For large, you can get to 20 gigapixels per second. So it's very promising. The issue is that we need a very high dynamical range. I mentioned already that it must be about 3 orders higher than in the initial image. So in total, about 12 orders. We also need to apply floating point corrections, and we need to work in floating point because otherwise scientists will not trust us usually. So the issue with floating points is that floating point operation will last for more than for several clock cycles, and our algorithm is designed to process exactly 1 pixel per clock cycle. This is fine if, for example, we are getting a series of target bins. Yeah, let's say that the floating point operation lasts for 4 floating point operation lasts for 4 clock cycles, and if the target bins are 4 clock cycles from each other, in case A, where is always it's fine. If they are closer, or for example, there is a case C when all intensities should go in the first bin. Yeah, then it also fails, like the simple algorithm. We can clearly solve it by some type of resorting, and in the case C, by some type of smart merging. So this is exactly what we are doing. We added a preprocessing, where we sort the values and match them. and this will solve the problem. So we are using a Bitonic sorter, that can be expressed in the means of historic arrays that fit FPGAs very good. As you can see, we are describing what tools we are using. We are using high-level tools like, for example, OpenCL or Synchronous Message Exchange, and which is a framework developed by Kenneth and Carl, and the students at Copenhagen University are implementing this a lot of imaging. Like image processing or sound processing algorithms with that. On top of everything, we have Python. So the code looks like C. I would mention one like technical thing. We can think about ratio between the data and the metadata or control data. For example, the raw data are 2 bytes, but the information that we need to store for the sparse metrics or the meta information is in total about 14 bytes. So the sparse metrics data or the metadata are much more than the input data. Because they are also large, they need to be in DDR memories, and this is causing troubles with bandwidth. This can be solved in 3 ways. We could calculate all the geometry on the FPGA, but then we would not be dividing physics from the computation. We could also use expensive hardware with expensive memories, but that is maybe not a good engineering solution. And the third solution is that this metadata are same for usually whole series of images. So we could process as several images simultaneously, and then we will revert the ratio. So here is the results, performance figures that we got for like Intel FPGAs with OpenCL. There is a medium board and large board. It can be seen that we achieved a pixel rate about 5.7 gigapixels, almost 6, like comparable with this V100, for example. And we have also enough bandwidth to cope with a 4 megapixel detector on 500 hertz. With this, we have this medium board achieved what we wanted effectively. That's already nice. Then we, with the large board, we have still a space to even double the number of processing pipelines. In this case,
are you almost done?
Yes, I am.
Okay.
So this is, I will skip our next steps. I will just say that similar activities are on other sides. It's Philip Lownarski is developing spot finding algorithm of FPGAs at the Polsher Institute. There is a publication about 3D tomography reconstructions on the same FPGAs as we are using. And of course, people are using FPGAs for effective and energy effective data processing on nano satellites, because we can launch today thousands of them. Thank you for your attention.
Thank you. Okay, we have time for questions. Actually, we have extra time because of one of the talks will not be happening. So we have a question. Why would scientists trust you more if you use floating point numbers rather than fixed point, which are then converted to floating point?
You are completely right with this. Like, first of all, we really need to go to floating points. We cannot be enough with integer arithmetics, because especially of these corrections and pixel splitting. Then why we should use fixed and floating points against each other? So honestly, because I am a high-level synthesis developer, I don't have much experience with fixed points. And what I can just say is that I need about 12 decimal orders of the dynamic range. And another possibility is with these FPGAs that we are using, the medium and large ones, we have floating points units there, or we can use even double, and it is integrated in the frameworks, so we don't care about that I should use a fixed set point arithmetics. Honestly, it would be for me more complicated than with floating point or doubles, which are even possible. And our algorithm works with floating points and doubles in the sense that it can process 1 pixel per clock cycle per pipeline. Yes, so it's just a convenience. I have no reason to switch to fixed points. That's like, well, why I should do it. Yeah.
Thank you. Okay, I think we probably should move on to the next speaker. We're going to move forward to Alan. Again, Manuel, would you like to take over?
Yes. So we're moving to the last talk. What was supposed to be the last talk, but it's maybe not the last talk today. So the speaker is Alan Peixinho. He's a machine learning and image processing specialist from the Brazilian Synchrotron Light Laboratory. And his current focus is on techniques to optimize algorithms for analysis of large images. And he's going to talk to us today about RemoteVis. It's an efficient library for remote visualization of large volumes using NVIDIA Index. So Alan,
Hello.
floor is yours.
Can you listen to me?
Yes, we
Great.
don't see slides yet, but we can hear you.
Let's go. I hope you
We
can
see the slides.
Oh,
Yeah.
great. So first of all, I would like to thank you for attending. As presented, I'm currently working on the Sirius Brazilian Synchrotron facility, and I'm here to present a solution we proposed to manage our data analysis pipeline we call RemoteVis. So in the past, our previous facility, the UVX, which was basically a second generation equipment that was recently deactivated. In there, we were able to generate volumes in the order of a few gigabytes, and the generated images are usually analyzed using commercial or sometimes open source solutions such as Thermo Fisher Aviso and ImageFiji. However, with the advent of Sirius or new fourth generation equipment, we're able to achieve a much higher order in the order of hundreds of gigabytes in a single image. And we can expand it even more when we're considering panoramic or for the image analysis. And our previously adopted solutions have shown to be unable to properly deal with the huge amount of data. So for this reason, we have studied alternative tools to cope with such scenario. Among them, we have Annotator, our in-house solution for image segmentation, general image processing, and Index, which is a proprietary image visualization tool developed by NVIDIA. In both solutions, they guarantee a high throughput, basically by leverage mostly of the processing to NVIDIA GPU cards. Our preference for Index is mainly based on its fast handling of volumes, and especially in its scalability, because basically Index is able to break the data in subvolumes that can be distributed among multiple GPUs in a node, and even to distribute this as well to multiple nodes in a distributed process system, which allows us to keep a near real-time handling even in our most demanding scenarios, where we are able to even visualize data in the area of at least 200 gigabytes with little to no problem. Another important point is that despite Index being a closed source solution, it still allows us to extend its capabilities by implementing plugins suited for our needs, which is especially important as we have many different bin lines for diffraction, tomography, and so on. And each one of these bin lines have their own specific needs, different processing of the data, different parameters to manipulate, and so forth, so on. I would also like to present a few use case that there's a proof of concept for the development pipeline. In this case, we have basically an example of a tomography image that came from a fluid flow and power analysis experiment. We have also adapted our pipeline to deal with point cloud handling, as for some of our bin lines, we do not generate a proper volume, but only a cloud points. In this scenario, we have also developed together with the bin line researchers exact kernel with a shading strategy specifically designed for this data in order to basically maximize the expressiveness of the data for the problem. In here, it's on. This was one of the most challenging data we have so far, both in terms of size and the problem itself. It's a tomography of a mouse heart, and I believe this one specifically illustrates well the benefits of analyzing the big portions of the volume regardless of its size. As with this analysis, the researchers could develop a much better insights of the structures of the heart, especially after we segmented cell per cell of this heart. Here I have an overview of the proposed solution. Our emitter stays all time basically receiving connections from multiple channels. All communication with this meter is done basically via WebSockets using a JSON or RPC protocol. And the meter is responsible basically for receiving, initializing and shutdown commands, while the hindering commands and other data exchanges basically done directly between the channel and index. And we so far are able to implement exchange of data, both between files, where we have a loosely file system with a considerably high throughput, as well as our RDMA solution that allows us to exchange that data directly between memory from our machines in the cluster, minimizing at most the usage of CPU. Our middleware is basically a piece of software receiving WebSocket JSON RPC connections, and it supports initialization of the process directly with the OS. But we have also devised a Slurm integration option where visualization instances they're idle for some defined time that we're still adjusting, are automatically disposed in order to guarantee a better resource allocation. In this scenario, each beeline has its own visualization queue, mostly dedicated for the on-site analysis, while we still keep a global queue for general purpose, mostly used by users that are doing more time-demanding analysis of previously acquired data, and so on. Many of our users were already familiar with Python Jupyter notebooks. For this reason, we have also implemented a Python wrapper for our C++ API in order to grant them the ability to visualize in a matplotlib-like solution where they were able to handle their analyzed data. Here they can basically use the whole Python ecosystem to visualize not only the acquired data, but also visualizing part of the information obtained with data processing, with general data processing. For the users that were attempting to visualize only file storage data, the most common users, we also have developed a full web option, as well as a command line interface that integrates with our API. And I believe one of the most important problems that we were tackling is basically that we wanted to solve the problem of on-site visualization, renting the users the ability to see the data while it's being acquired. For this reason, we provided a direct channel with our detector software, so the users can visualize, even apply some pre-processing. They're basically implemented as index plugins. And with this, we were able, despite we still adjusting a few things, we're able to have the beeline users to process the fine tuning of parameters, as well as detecting a few problems during the process of the data generation acquisition. Finally, we have also provided a two-way communication with our segmentation tool, where the user can basically select a few regions of interest that can be annotated. These regions of interest can be processed and then sent back to the rendering tool. These users can also train segmentation machine learning modules and deep learning models that can, after finishing the modeling process, be sent back to Index to improve even more the quality of rendering data analysis. For now, we have been able to share the deep learning trained models, basically using a TensorRT version, a TensorRT optimized engine version of our models. But we also pretend in the future, it is in our plans to implement basically to implement a generic pipeline for machine learning and allow the users to share also their classic machine learning models trained for the data. I believe that's it.
Many thanks, Alan, for the very nice presentation on visualization, which is sometimes not taken into account in data analytics, but it's a very important part. So are there any questions to Alan? If not, I have one quick one. So what you have shown, how much this is tied to the NVIDIA system, how much this could be reused with a different GPU bucket.
I'm sorry, I could not listen well. Let me change here.
Sorry.
Can you repeat, please?
Yes. So what you have shown seems to be very tied to NVIDIA. Is it like that? Or one can replace NVIDIA, the NVIDIA system by a different vendor or a different solution?
We have considered this in the past. Basically, we have kept the backend handling quite open to change platforms, but now we are putting some second thoughts on this because basically the NVIDIA index is being able to assess exactly what we're looking for and especially the scalability. So we're probably sticking with NVIDIA index.
Okay. Are there any other questions? I don't see any.
I cannot find a way how to put a question. Could I ask?
Okay.
Directly?
Yes, sure. Yes, go on.
Can we find your work somewhere? Like, is it in public repos or is it going to be? Yeah.
Sorry, I think I'm having problems with the quality of.
Maybe I missed some links. Yeah. Can we find your software and your solutions somewhere available? Like, or it is not yet available for public purposes or release?
For now, we still are developing it in-house. It's a closed solution, but I believe it's in our plans to make it an open source package. Sure. To be able to distribute and also get collaboration from many developers across the world.
Okay. We have 1 minute for another question. What? No, so if not, let's thank Alan again. Thank you, Alan.
Thank you.
Okay. And we are moving now to the last talk of the session, where it was originally the second talk. I think finally Ali has managed to connect. Ali, are you there? Yeah, you have to unmute. Yeah.
You hear me?
Yes, we hear you.
Yeah. Hi, everybody.
Okay. Okay. I will introduce you if you don't mind. and then we can. So Ali Khalegi, he's from the Iranian Light Source Facility, from the Institute for Research in Fundamental Sciences of Tehran. And he's a data scientist, a member of the control unit of the light source. So, yeah, please, Ali.
Okay, thank you. Can I have my presentation here? Can I have it?
Can you share it, or we have to share it for you?
Yeah, I share it. But
okay. Yeah. You should have a share button. Normally it's green, I think.
yeah. I share it by myself, or you?
Yes, if you can, you share it. If you cannot, I can share it for you.
Yeah, could you share it, please?
Yes. Okay. So do you see it?
Yeah, perfect. Hi, everybody. I present to you a literature review of the works of using machine learning in synchrotron. In general, we want to know what happened in synchrotrons, and yeah. And can I control it? Can I go to next page?
You'll have to ask me, Ali.
Yeah,
I will do it for you.
okay, thank you. So what are the challenges in new generation of synchrotron? Lower emittance, higher beam stability, and data flood. You know, each day, a synchrotron produce peta data. So we have a data flood. Next page, please. So what's the machine learning advantage in synchrotron? As you know, reducing the fluctuation of the electron beams, stabilizing the photon beams, using data flood, harnessing the brightness of light source, supporting efficient monitoring and fault detection, optimal setup using automatic alignment, providing feedback from speedy physics-based simulation, as we found in literature in general. And what's the challenge of using machine learning in synchrotrons? We need the long-term data storage and transfer, as well as the demand for data analysis pipelines, the requirement for instant feedback. We need the software package to control the wide data generated in experiments, and also the lack of remote data analysis workflow, and the use of distributed resources for machine learning purpose. Next slide, please. And there are some solutions, a cross-facility solution that can accelerate creating a data processing platform at synchrotrons. Some study reports that the big data center is required for management of processing. In a study at 2017, we saw 89% of participants were not familiar with big data according to the and according to our study. But now I think it's more than better. Next page, please. As you know, I don't want to define to talk about machine learning. You know better than me. As you know, machine learning is widely used to make prediction or decision, a subfield of artificial intelligence, and the process of making a mathematical model using sample data, famous as training data. Next page, please. Normally, we use different machine learning techniques in synchrotron: supervised learning, we saw unsupervised learning, reinforcement learning, semi-supervised learning. And also we saw some case multi-level machine learning. Next page, please. And clustering and neural networks. Clustering is categorized as supervised learning, so as a unsupervised learning, so we don't need the label. And deep learning now almost synonymous with machine learning to the public. In neural network, we use hidden layer to find and explore complex data's pictures. More than more in synchrotron, we use neural networks. Next page, please. Neural networks in synchrotrons have attract attention due to their ability to facilitate image-centric big data science. Neural network can explore nonlinear and dynamic behaviors, image-based diagnostics, produce high-quality output more quickly, and reduce the amount of data that must be collected, can be easily integrated into existing data pipelines in real time, enable better quality image in the earliest stage of data acquisition. Next page, please. And in CERN, they use machine learning for beamline commissioning, optimization of beam, detection of collective beam instability, and heating detection from pressure reading, and numerical simulations. Next page, please. And in CERN, they've developed an automated software for beam commissioning of the collimation system using machine learning algorithms. They've arrived to decrease really the alignment time perfectly. Next page, please. And in NSLS2, they've developed the Blue Sky suite, a collection of Python libraries for data acquisition and management. All data and metadata generated during an experiment can be emitted in real time to order process in the form of document and Python dictionary with comprehensible schema. The generated documents can be distributed locally or over network. All beamline hardware is accessed via a library called OPIDE, and the access to historical data is through an API called Data Broker. Next page, please. And also they use reinforcement learning methods for optimizing beamline operations. Python-based Blue Sky suite of data acquisition, demonstrating the functionality by solving a classical reinforcement learning problem. And CARPAL in Blue Sky environment. Use reinforcement learning methods for maximizing data quality across multiple samples, a different scattering string within a limited time window. Thank you. And in advanced light source, delivering light to loss of beamline is one of the old problems in synchrotron light source facility. So fluctuation affect beamline's performance, and fluctuations are reduced using correction and calibration. And in advanced light source showed that neural network algorithms can predict noisy fluctuation in the size of beam generated by light sources. Neural networks can correct change before they occur. So it means feed forward versus feedback correction. We saw in the other area also. The algorithm learns the complex nonlinear relationship between the ID settings and vertical beam size and make correction. And neural networks stabilize the vertical beam size at 0.2 micrometer. Next page, please. In SSRL, they've developed the T-port platform to implement online optimization. As you see in the schema, the architecture of T-port, fast switching between the simulation evaluator and the experimental evaluator, and T-port as a unified interface for the optimization algorithms. They've developed two machine learning-based global optimization algorithms for storage ring nonlinear beam dynamic optimization using multi-generation Gaussian process optimizer to solve multiple objective optimization problem. And next page, please. In BESI2 in Germany, they've used supervised learning model trained only with 185 accelerator variables, excluding previous lifetime measurement to predict beam lifetime in a time series fashion, implementing the prototypes to self-tuning of machine parameters in different optimization case like injection efficiency and orbit correction using deep reinforcement learning agents. Next page, please. And in delta synchrotron, they've used conventional feed-forward neural networks trained on measured orbits to apply local and global beam position correction to the 1.5 GeV surgery. They've applied machine learning techniques as an alternative approach for automated orbit correction. Next page, please. And FRBL identified four main areas that machine learning algorithm can be helpful, including virtual diagnostic, optimization and operation, beam optic correction, instrumentation, fault detection. Reinforcement learning is suitable for solving complex control tasks. Unsupervised learning is helpful for anomaly detection tasks, such as detecting instrumentation defects. And next page, please. We have a short sentence of this article review. Implementing a game like
You have 2 minutes left, Ali.
2 minutes?
Yeah, 2 minutes.
Okay. Okay. Implementing a game-like project defining a reward scheme to train, and we reviewed the good work, but they are ad hoc based on different beamlines and synchrotrons. We can see the lack of integrated platform. Implementing remote data analysis workflow and use distributed resources. For Python, a standalone platform can be implemented more easy and rapidly. Next page, please. I jumped some. Yeah. Deep learning has been considered mainly due to their ability to explore nonlinear and dynamic behavior and facilitate image-centric big data science. But I jumped this slide, just the last slide, please. Yeah. And as a resume, the stability of machine learning method has been clearly shown for beam energy, brightness, stability, etc. There are many efforts to provide data management platform for machine learning model. Generally, in large experimental facility, unifying machine learning ready solution is needed. Machine learning algorithms should have the capability to be used online by providing online powerful data analysis platform and feed-forward correction, evaluation, and optimization more beneficial than feedback ones for many synchrotron practice. So in future research, the aim will be to present a more comprehensive sentence with more detail on how to use machine learning in synchrotron. Thank you for attention.
Many thanks, Ali, for this nice overview of machine learning techniques and accelerators. Is there any question for Ali? We have time for maybe for one quick question, maybe two, depends on the length. No questions? I don't see anything on the chat.
I don't see any questions either. All right.
Maybe a quick one. Oh, okay, so maybe let's move on. It's already time. Yeah. So we conclude then.
Okay, yeah, I think this should, thank you to all of our speakers. Okay, thank you to all of our speakers. If anyone does have any questions, please feel free to reach out to the speakers through Huva to make contact. So this concludes today's data analytics session, and we'd like to hand it over for the workshop summary being chaired by Yingbing. Thank you.
Yes, thank you, Sira.
Thank you, bye.
Okay, and next is workshop summary. We have 5 workshops last Thursday and Friday. The first is Linux distribution and ecosystem evolution in control system workshop. Okay, Thomas, please share your desktop. Thanks.
Can you see my desktop and my video? Yes.
Yes.
All good. Okay, so I've been asked for a quick summary of the workshop. So I'm Thomas. I've been working at CERN for the past 10 years, 8 years in IT and 2 years in the BIM department. And I will go through a few numbers first. So we had 195 registration, around 50 institutes. And on Thursday, we got around 120 participants. So it was very nice. Unfortunately, we have one council talk. And we split the talk between 3 sessions that I will be describing in a second. First, I wanted to come back on the motivation. So our motivation was to see what people use in control systems and in different labs around the distribution, the Linux distribution. Typically, we know a lot of people are still using CentOS. So this cloud is taken from the survey we sent before the workshop, and we can see that CentOS is still one of the main OS used, and last year, after the announcement that Red Hat will be shifting focus from CentOS to CentOS Stream, we had to review our possibility on the server workstation, but also on the industrial PC. And this work already started plus a bit before. So the first session was about CentOS. So it was a presentation about Ben Morris at CERN that present what was going on at CERN, because it's not directly associated to control, but we got a lot of people asking for feedback on what was the plan at CERN. So the takeout of this is for several workstation, we'll be using CentOS Stream 8. There's a lot of investigation on what is used for Red Hat Enterprise Linux for academic license offer as well. So this is something that we'll be looking at in the next month. And the community is always evaluating other rebits as well, which is Rocky Linux and Alma Linux. And finally, nothing is set in stone for the future. And so this is quite important. And one point I wanted to highlight is there will be a joint announcement for people not close to all these different communities between Fermilab and different app-lab in the next days, weeks. Finally, we had a CentOS board member. So I am one of the CentOS board member, and also True join us to reply questions from the community. So that was quite interesting for participants. Linux distribution in control. So Federico Vaga presented this second session about what could be done at CERN around industrial PC, and we had a lot of feedback on the different how we can improve the workflow that we are using and how we can be better at it. There's an ongoing evaluation that will be finished next year about operating system, and please look at the presentation for the detail. And also here, the interest was on how we can distribute software and all the related security challenges around that. So this is quite important subject, and we hope we can continue to discuss around that in the future. And it's always a good thing to have a clear way to distribute operating system images for different use cases. Finally, I did a presentation about Nix and NixOS, which is an OS based on new concept, and it was quite interesting to see that people in the audience were interested and are looking at it. So our friends from CEA are looking at it, and this was very, very interesting, and we got good feedback. And we also have a presentation about what is going on in the Fedora Silverblue. It was just a slide about what is going on in the Fedora Silverblue and CoreOS, which want to achieve the same as NixOS in a different way with RPM packaging. So the last slide for me is just to remind you all the link and to say thank you to everybody who attended. We have created a room in matrix.org. This is a chat system thanks to Sia Sakley colleagues that created it. And this is where we'd like to give you feedback on the future and to see what is going on. So I will be sending the link to the participants, but feel free also if you're interested in this Linux distribution discussion to join. And that's it for me. Thank you.
Thanks for organizing the workshop. Thanks.